Okay guys, welcome back to Analog Circuits. So we have been looking at ideal op-amp in negative feedback, and mainly it is about the application of something called virtual short. And you also know how to identify the type of feedback in any given op-amp circuit. Okay. Uh, so in the afternoon session, what did we mainly look at? I think we solved a lot of circuits, right? Yes. So in this session, what we'll do is to try and come up with different types of controlled sources using the op-amp. Okay. See, the op-amp itself, we know, is a control source. Op-amp is what? A voltage amplifier, right? Op-amp, all of you know, it's a voltage amplifier. And any voltage amplifier is nothing but a voltage controlled voltage source. So op-amp itself, we know it is what? A voltage controlled voltage source. Now what we'll do, using this op-amp, which itself is a voltage controlled voltage source, we'll try to design, or we'll try to make the other three dependent sources. What are the other three dependent sources? We have VC CS, we have CC CS, we also have CC VS. Right now we only have the op-amp, which is what? A voltage controlled voltage source. And using this op-amp, we'll try to make the other three, controlled sources. That is the agenda for the initial part of this session. And depending on how much time is available, we'll also take up the discussion on finding the input and output resistances of any given amplifier. But for now, we'll try to understand how one can make any type of dependent source using the op-amp. Okay. Let us look at our first circuit. All of you please note down this circuit. This is R1, this is also R1, this is R2, this is also R2, but this is what? The load resistance. This is ground. So here you can say we have this load resistance. This is what? The load resistance. And the current through the load resistance, we will call it the load current. So what is the input source driving this circuit? There is the input source Vi. Okay. And what are you supposed to find? We are supposed to find the load current, which is the current flowing through the load resistance RL. Okay. So what is our goal? It is to find an expression for the load current. So in this circuit again we have the op-amp. Of course the op-amp will be ideal. And along with the op-amp, there are four resistors. Two resistors, each of value R1 at the top. And at the bottom, again we have two more resistors, each of value R2. So at the top, R1 and R1 both are identical. Even at the bottom, R2 and R2 both are also identical. And then we have this load resistance through which the current is what? IL, and that is what we are trying to find. So first and foremost, if you observe the output of the op-amp, this is what? The output of the op-amp. It is connected to minus input terminal. It is also connected to what? The plus input terminal. Whenever that is the case, first we need to decide whether the op-amp is in negative feedback or not. Yes. So here also, first let us try to find out the type of feedback. Let us try to find out the type of feedback. Okay. How do you find the type of feedback? Okay, before that, I just make a copy of this. Okay. So what is the method of finding the type of feedback? Whenever the output is connected to both the input terminals, always at the output of the op-amp, you should apply some Vt, and then you should try to find V minus and V plus in terms of Vt. And while doing so, you have to make all the other independent sources 0. What is the only independent source in the circuit? It is this input voltage source Vi. If you make any voltage source 0, it becomes what? A short circuit. And if this becomes a short circuit, the potential at this point will become 0. Again, we know for ideal op-amp, both the input currents will be 0. What is the voltage at this point? Vt. What is the voltage at this point? Also Vt. Now at the top, because this current is what? 0, clearly these two currents will be equal, which means at the top R1 and R1 both are in series. Between what? Vt on the right and 0 on the left. Whenever resistors are in series, you can directly write the voltage at the common node. Would it not be Vt by 2? Because Vt into R1 upon R1 plus R1, which is Vt by 2. In the same way, we must also find V plus, and then we should compare V minus with V plus. Depending on whichever is bigger, that will be the type of feedback. Okay, coming to the bottom part of the circuit. See, if you observe, please look at R2 and RL. Are they not in parallel? I am saying what? R2 and RL, they are in parallel. R2 and RL, they are in parallel. Parallel means what? Both the elements should be connected between the same 2 points. In fact, if you look at this R2, is it not connected between this point and ground? And if you look at this RL, it is also connected between the same point and ground. Okay. So I am talking about this R2 and the load resistance. Both are connected between the same point and ground. So I hope all of you agree that R2 and RL both are in parallel. If two resistors are in parallel, they can be clubbed into what? A single resistance. Okay. Whose value of resistance will be what? R2 into RL divided by R2 plus RL. So it is as if you combine these two resistors into what? One single equivalent resistance. And that single equivalent resistance, will it not be in series with this R2? Yes or no? So it is like this. So you got Vt here. Then we have one resistor R2. Then the remaining two have been clubbed into what? A single resistance of value R2 parallel RL. And this point is what? The plus input terminal, where the voltage is what? V plus. You see, please look at this. First we have Vt, then we have R2, then we have R2 parallel RL, and then we have ground. Clearly, this and this both are in series. We can apply voltage division. So at the top we have R2. At the top we have R2. At the bottom we have R2 parallel RL. You know the value of R2 parallel RL will be less than both R2 as well as RL. This is a very simple fact. If any two resistors are in parallel, then the equivalent resistance will be less than both the individual resistances. So we do not know what the exact value of R2 parallel RL will be, but for sure this R2 parallel RL will be less than R2. Now at the bottom, whatever R2 parallel RL we have, if it is R2, at the top already we have R2. So at the bottom also, if the resistance is what? R2, then V plus will be equal to what? Vt by 2, because both are identical. So voltage at the common node will be half of Vt, that is what? Vt by 2. But here what is our case? At the bottom the resistance is what? Not R2, it is less than R2. If it is R2, V plus will be what? Vt by 2. But at the bottom we have what? R2 parallel RL, which is less than R2. So you tell me, V plus will be Vt by 2 or less than Vt by 2? Definitely it will be less than Vt by 2. because at the top we have R2, but at the bottom we have a resistance which is smaller than R2. If it is R2, then V plus will be Vt by 2. But if it is less than R2, then V plus also will be less than Vt by 2. So already we know V minus is what? Vt by 2. And now we have come to find that V plus is what? Less than Vt by 2. Once you know V minus and V plus, you have to compare V minus with V plus. V minus is what? Vt by 2. V plus is what? Less than Vt by 2. Clearly V minus is greater than V plus, which means the feedback is what? Negative. The feedback is what? Negative. So in this way, we are able to decide that this op amp is also in negative feedback. In fact, this op amp will be negative feedback for any values of R1, R2 and RL. We did not impose any kind of condition on the values of R1, R2 and RL. So for any value of R1, R2 and RL, op amp will be in negative feedback, which means from now we can use virtual short to find the actual thing. What is the actual thing? It is to find the load current. Okay. So once again, I've drawn the same circuit. Now let us find the load current using what? The principle of virtual short. Now what is that virtual short? This point, which is the minus input terminal, or let me call this point. This point is what? The minus input terminal. This point is what? The plus input terminal. Okay. Let me call this A. Let me call this B. Let me call this point as C. If you look at R1, if you look at this R1, is it not between A and C? And if you look at this R2, is it not between B and C? So for this R1 and for this R2, which point is common? C is common. Yes or no? For these two resistors, C is what? Common. Whereas the other 2 points, they are not common. Okay. A and B are 2 different points, but they are at same potential due to what? Virtual short. Now if I ask you what is the drop across this R1, you would say it is what? A minus C. If I ask you what is the drop across this R2, again you would say B minus C. But then A and B are identical in terms of potential. So is it not that A minus C will be same as what? B minus C, which means the drop across R1 is same as what? The drop across this R2. This is purely due to what? Virtual short. So this R1 and this R2, they are not connected in parallel physically, but because of virtual short, it is as if they are connected in parallel. So they have the same voltage drop. I hope this argument is clear. The fact that this R1 and this R2 both are going to have the same voltage drop. There is an important observation which can be used in solving many circuits. Okay. So just erase everything. Okay. Now look carefully. What is this voltage drop? This is what? The drop across the load resistance RL, through which the current is what? IL. So is it not IL into RL? So what is the voltage at this point? It is going to be IL times RL. Which point is this? The plus input terminal. So the voltage at the plus input terminal is what? IL RL. Then from virtual short, the voltage at minus input terminal will also be IL RL. What is the voltage at this point? It is VI. Okay. What is this current? Left side minus right side divided by R1, which is VI minus IL RL by R1. Again, we know for ideal op amp, this current and this current, both being the 2 input currents, will be equal. Now because this current is what? 0, this entire current will flow through the other R1 from left to right, resulting in a voltage drop of what? What is the voltage drop across this R1? This current multiplied with R1. So VI minus IL RL divided by R1 into R1. R1 will get cancelled out. Directly we can write the voltage drop across this R1 as what? VI minus IL RL. VI minus IL RL. Earlier I said this R1 and this R2 both will have the same voltage drop due to virtual short. So we can write down the same voltage drop across this R2 as well. Vi minus IL RL. Vi minus IL RL. Now let us call this current as I1. Let us call this current as I2. Look at this point. At this point, how many currents are flowing? I1 is flowing away from this point. IL is also flowing away from this point. Even I2 is what flowing away from this point. And no current is entering this point. Three currents are flowing away from the node and no current is entering. So sum of the three currents is what? 0. So writing KCL at this point will give us what? I1 plus I2 plus IL equal to 0. Now what is this I1? Current through R2 from this point to ground. So Ohm's law, IL RL minus 0 divided by R2 plus what is I2? Drop across this R2 divided by R2, which is Vi minus IL RL divided by R2. And then we have the third term, which is just IL, and this sum is what? 0, because we are writing what? KCL. Now the first term, I'll write it as it is, IL RL by R2. Second term, I'll split it into two separate terms. First is what? Vi by R2. Next is what? Minus IL RL by R2 plus IL equal to what? 0. So if you observe, IL RL by R2 minus IL RL by R2 both will get cancelled out. So from here directly we'll get IL, that is a load current, to be this minus Vi by R2. This is the final expression for the load current. IL equal to what? Minus Vi by R2. Okay. So all of you please note it down up to this point. Okay guys, again look at the screen, all of you. If I ask you, what is this yellow box? You would say it is what? A current source, because clearly inside this yellow color box, we just have the current source of value Is. Is it an ideal current source or a non-ideal current source? Clearly it is what? Ideal current source. Had it been a non-ideal current source, inside the box, we would also have an internal resistance Rp connected in parallel. But in whatever box I have drawn initially, there was no such internal resistance in parallel. We only had the current source, but not that resistance Rp. Okay. So this box, you should say it is what? Ideal current source. Now across this box, let us connect an arbitrary load resistance RL. Let us call the current through the load as what? IL. Now in this particular circuit, the load resistance, is it not directly in series with the current source? Any two elements in series will always have the same current. Yes or no? So IL will be equal to IS. Yes or no? Because the load resistance, it is in series with the current source. IL equal to IS. Is IL equal to IS for any value of RL? Again, yes, because after all, the load resistance, it is in series with the current source. Whatever be the value of load resistance, the current through the load will always be equal to what? IS. So across this current source, whether you connect 1 ohm or 1 kilo ohm or 1 mega ohm, always the current through the load will be equal to what? The value of the current source, that is IS. So here the point is what? IL equal to IS for any value of RL. So whatever be the value of the load resistance, IL will be equal to what? IS. So can we say the load current is what? Independent of load resistance? Yes or no? Irrespective of the value of the load resistance, always the load current will be equal to what? The value of the current source, because the load is directly connected across what? An ideal current source. So load current IL is what? Independent of the load resistance RL. This is the observation that we have to make. The load current is what? Independent of the load resistance. Okay. So when will the load current or the current through the load be independent of the value of the RL? Only when the load is connected across what? An ideal current source. Okay. Similarly, the other case we can have is what? This. This time, if I ask you what is this yellow color box, you should say this yellow box is what? Ideal voltage source, because inside the box there is only one element, and that is what? A voltage source. And why is it ideal? Because there is no resistance in series with the voltage source and so on inside the box. So definitely it is what? Ideal voltage source. Now across this box, which is an ideal voltage source, let us connect some random value of load resistance, and let us call the voltage across the load as what? VL. VL is what? The load voltage. Now if I ask you what is the value of VL, you will directly say it is what? VS, because the load resistance, it is directly connected across the voltage source. If one element is directly connected across any element, then those two elements will be in parallel. They'll always have the same voltage drop. Okay, in this circuit, the load resistance, it is not only in parallel with the voltage source, it is also in series, but that's a different thing. If you are talking about voltage, we should look at if elements are in parallel. Okay, so here VL equal to VS. Can I say VL equal to VS for any value of RL? Because whatever be the value of the load resistance, because the load resistance will be in parallel with the voltage source, always the value of the voltage source will directly appear across the load resistance. So just like the earlier case where we said IL equal to IS for any value of RL, in the current case I can say VL equal to VS for any value of RL. So across this voltage source, whether you connect 1 ohm or 1 kilo ohm or 100 kilo ohms, always the load voltage will be equal to what? The source voltage. So can I say the load voltage in this case is independent of the load resistance, just like the earlier case where the load current is independent of load resistance. In this case, the load voltage is independent of the load resistance. So these are like two special cases. So in one case, it might happen that the load current is independent of load resistance. Maybe in some other scenario, it might happen that the load voltage is independent of load resistance. So when will these two cases occur? Load current will be independent of load resistance only when the load is what? Directly connected across an ideal current source. And when will the load voltage be independent of load resistance? Only when the load is connected directly across an ideal voltage source. Only in these two cases, either the load current or the load voltage is going to be independent of the load resistance. Okay. So with this idea, let us go back to our circuit for which we ultimately found the load current and it came out as what? Minus VI by R2. Let us reflect on the result. Okay. So what did we get? This, that IL is equal to what? Minus VI by R2. What is this IL? It is the current flowing through this load resistance. And look at the expression for IL. IL, it depends on what? VI. It also depends on the value of R2, which is either this or this. Whereas IL is what? Flowing through the load resistance RL. So in the expression for IL, is there any RL? There is no RL. There is VI, there is R2, but there is no RL. So if the expression for IL does not contain RL, that means what? IL is independent of RL. So this means IL is what? Independent of RL. Or I can say the load current is independent of load resistance. When will the load current be independent of load resistance? Load current will be independent of load resistance only when the load is what? Connected across a box, and that box should behave like an ideal current source. So coming back to our case, where again the load current is what? Independent of load resistance. This means what? With respect to the load, with respect to the load resistance RL, the rest of the circuit, that means what? This entire thing behaves like ideal current source. That is how you have to understand this result. Because the load current is independent of load resistance. With respect to load or from the load point of view, the remaining circuit will behave like what? Ideal current source of how much value? Minus VI by R2. Understood? But then this IL, that is the current flowing through the load, does it not depend on this applied input voltage VI? Which means in this circuit, if you vary the applied input voltage, does it not directly affect the value of the load current? So changing the voltage here is going to affect the current flowing in this branch. So one voltage controlling current in another branch. What behavior is this? One voltage, which voltage? VI, the applied input voltage, is controlling how much current will flow through the load resistance. So one voltage controlling another current. What is this behavior? Is it not voltage controlled current source? That's all. So this circuit with respect to the load behaves like ideal current source, but then the value of the current depends on the applied input voltage. So in a way, that input voltage is controlling how much current will flow through the load. So it is what? Behavior voltage controlled current source. That's it. Voltage control current source. Very good, Srinivas. So what did we accomplish here? We started off with the op amp, and we know the op amp itself is what? A voltage controlled current source. Yes or no? Sorry, voltage controlled voltage source. I'm sorry. The op amp itself is what? Voltage controlled voltage source. So using this op amp along with proper negative feedback, we came up with a circuit which behaves like a voltage controlled current source with respect to the load. See, you should not call the entire circuit is what? Voltage controlled current source. No, that is not the correct statement. With respect to load, the rest of the circuit that is within this box will behave like a voltage controlled current source. So using an op amp which is VC Vs along with negative feedback, we are able to come up with another control source which is voltage controlled current source. Understood, right? Yes. So it should be clear why current source in the first place. Why current source? Because the load current is what? Independent of load resistance. So if at all we did the analysis and in the end we find that the load current depends on load resistance. If at all the load current IL depends on RL, for which the expression for IL should contain RL, then we should not say the circuit behaves like ideal current source. Only if load current is independent of load resistance, only then with respect to that load, the remaining circuit will behave like ideal current source. I hope this point is clear. Okay. Let's look at another circuit. Okay, so this is our next circuit. Once again, the op amp is what ideal, and here you can see we have the load resistance through which the current is what designated as IL. Again, the question is what to find the expression for IL, and from the expression for IL, we will try to understand how the circuit will behave with respect to the load. Okay, but before that, we have to decide whether or not the op amp is in negative feedback, because here also, if you observe the output of the op amp, it is connected to minus input terminal, it is also connected to plus input terminal. So first, let us try to decide the type of feedback. Okay. So how do you decide the type of feedback? At the output, we need to apply a signal, we'll call it what Vt, and then we should find V minus and V plus in terms of Vt. And while finding the type of feedback, every other independent source, you have to make it zero. Here, there's only one independent source in the form of this Is. If you make it zero, it becomes what? Open. Or this current, you can say it becomes zero. Okay. So if you apply Vt at the output of the op amp, look at this Vt. Is it not directly connected to the minus input terminal? So what is the voltage at the minus input terminal? It would be Vt. Okay. What is this current? Ideal op amp input current is what? Zero. Because these two currents are zero, we can directly say even this current will be zero. Even the drop across this R2 would be zero. Now because the current through this R2 is what? Zero. I think I have some problem. Okay, I think I have to redraw this circuit. What is it? I think this was R2, this was R1, this was the load resistance RL, through which the current is what? The load current IL. And then driving this circuit is a current source of value IS. And the goal is to find IL. Is to find what? IL. So I was saying what? That first we need to decide the type of feedback. Okay. So to find the type of feedback, let us apply Vt at the output. So because the output is directly connected to what? The minus input terminal, even the voltage at the minus input terminal would be Vt. and you have to make this current source 0. So this current will be 0. This current anyway will be 0 because of the op-amp being ideal. Okay. So even this current will be 0. So these two currents will be equal. So there will be some voltage division. So the voltage at this point, would it not be something less than Vt? Yes or no? Because of voltage division, the voltage at this point will be something less than Vt. What is the drop across this R2? It is 0. If the drop across this R2 is what? 0. This point and this point both will be at same potential. So already we know the voltage at this point due to voltage division is what? Less than Vt. So even the voltage at this point would also be less than Vt. That's all. So what is V minus Vt? What is V plus? It is less than Vt. So V minus is Vt and V plus is what? Less than Vt. So clearly V minus is greater than V plus, which means the op amp again it is in negative feedback. So we can use virtual short and so on. So now let us make use of virtual short to virtual short to find the value of the load current IL. Just give me a minute, guys. Shama. Okay, I think now we can continue with the lecture. So we have found that in this circuit, the feedback is what? Negative. Now the goal is what? To find the load current IL. Find the load current IL using what? Virtual short. You see, please look at the screen. What is this current? 0. What is this current IS? Now because this current is 0, even this current will be what? Is. So what is the drop across this R2? It is Is times R2. It is Is times R2. Now again we need to make one observation. Let me call this point as A. Let me call this point as B. Let me call this point as C. Now if this is B, then what about this point? This is also B. Yes or no? Yes. Because this point is directly shorted to this point. If that is B, then this is also B. Now what is the drop across this R2? Is it not A minus C? What is the drop across this R1? Is it not B minus C? Now what is the relation between A and B? Are they not at the same potential because of virtual short? So A equal to what? B. A equal to B, which means A minus C equal to what? B minus C. In other words, this R2 and this R1 are going to have the same voltage drop. Yes, because this point is what? Common to both R1 and R2, whereas points A and B, due to virtual short, they are at same potential. This R1 and this R2 both are going to have the same voltage drop. It is as if they are connected in parallel. Okay. Okay, now what is this current? 0. What is this current? Is. What is this drop? Is times R2. What is this drop? Like I just explained, even this drop will be what? Is times R2, because R1 and R2 will have the same voltage drop. So what is the current through R1? Ohm's law, drop divided by resistance Is R2 by R1. That's all. Now at this point, how many currents are flowing? This current is entering, this current is also entering, whereas IL is what? Leaving. Let us apply KCL at this point. So if you write KCL at this point, sum of these two currents is equal to what? The load current. Or IL equal to what? Is plus Is R2 by R1. IL equal to what? Is plus Is R2 by R1. Yes. This can also be written as Is times 1 plus R2 by R1. Is times 1 plus R2 by R1. Even in this circuit, what is this load current? It is the current flowing through this load resistance. And if you look at the expression for the load current, it contains what? Is, which is the input current source, and then resistors R1 and R2, but there is no RL. So in the expression for the load current, there is no RL. There is no what? There is no RL. Sorry. There is no RL. In the expression for IL, if there is no RL, again, does it not mean that the load current is what? Independent of load resistance. So even in this circuit, the final observation is what? That the load current is independent of the load resistance. IL is independent of load resistance. In any circuit, if the load current is independent of load resistance, it means what? With respect to the load, the remaining circuit will behave like what? Ideal current source. Yes or no? So with respect to the load, the rest of the circuit, that is this circuit, behaves like ideal current source. Behaves like ideal current source. Let me again write the expression for IL, which is Is times 1 plus R2 by R1. So what is the point to be noted here? That the load current, does it not depend on Is? Is is what? The value of this current source. So if you vary the value of Is, even your load current will vary. So varying the current in this branch will affect the current flowing in this branch. So is it not that current in one branch is affecting the current in another branch, what behavior is it? Is it not the behavior of current controlled current source? That's all. So how does this circuit behave with respect to the load? This circuit behaves like a current controlled current source. Okay. Again, how did we make this current controlled current source? What building block has been used in this circuit? Again, the op amp. And the op amp itself is what? A voltage controlled voltage source. So once again, using the op amp, which is a voltage controlled voltage source, along with negative feedback, we are able to make a current controlled current source. So earlier, using the op amp, we made what? A voltage controlled current source. Now, using the same op amp, we made a current controlled current source. And both the circuits, we have employed what feedback? We have employed negative feedback. Okay. Let's look at another circuit. The circuit also contains what? An op amp, which is ideal. And then we have this load resistance across which the voltage drop is what? VL. So VL is what? The load voltage. Okay. So what is the question here? It is to find the load voltage. In the previous two circuits, we found the load current. This time, we will try to find the load voltage. So first question, is the op amp in negative feedback or not? Directly we can say it is in negative feedback because the output of the op amp, it is connected only to what? The minus input terminal. There is no doubt that the op amp is in negative feedback. So we can use virtual short and so on. Now what is that virtual short? V plus equal to V minus. What is V plus 0? Because the plus input terminal you can say is directly connected to ground. Now because V plus is 0, even V minus will be 0. So what is the potential at this point? 0. Now for ideal op amp, the input current is what? 0. What is this current? IS. So from KCL, even this current is also IS. So what is this current? Also IS. Now if you look at this RF, current through RF is flowing from right to left. So right side will be plus, left side will be minus, and the value of the drop will be the current multiplied with resistance, IS times RF. Now let us go from this point to this point. Let us go from this point to this point. This point is what? 0. Then you go from minus to plus, you add the drop, 0 plus IS RF, which is IS RF. Understood? That's all. So what is the voltage at this point? Also IS RF, because everything is what? The same node. Okay. Now what is the expression for the load voltage? This load voltage, is it not the potential difference between this point and ground? Already there is what? IS RF. So here the load voltage VL is equal to what? IS RF. Now if you look at the expression for the load voltage, it contains what? IS. It also contains RF, but there is no RL. There is no RL. That is what? Load resistance in the expression for the load voltage. So if the expression for VL does not contain RL, does it not mean that VL is what? Independent of RL? In what circuits or in what situation the load voltage will be independent of load resistance? Only when the load resistance is directly connected across what? An ideal voltage source. That means what? In this circuit, because the load voltage is what? Independent of load resistance, this circuit with respect to load behaves like ideal voltage source. Okay. So let me draw the same circuit once again because I forgot to copy it. So here is our actual circuit. And because the load voltage is what independent of load resistance, with respect to load, the rest of the circuit behaves like what? Behaves like ideal voltage source. In the previous two circuits, with respect to load, the circuit behaved like ideal current source because in the last two circuits, the load current was independent of load resistance, whereas in this circuit, it is a load voltage that is independent of load resistance. And also, if you look at the load voltage itself, does it not depend on IS? That means what? If you vary this current IS, even the load voltage will get affected or it will also vary. So this current, yes, this current is controlling this voltage drop. One current controlling another voltage. Is it not a current controlled voltage source? So what is the behavior of this circuit with respect to the load? Current controlled voltage source. Current controlled voltage source. That's all. So how did we make this current controlled voltage source? Again using the op amp, which itself is what? VC, VS, voltage control voltage source. So look at this. What did we achieve in the last three circuits? We were able to make one type of controlled source. First we made VC, CS, then we made CC, CS, now we have CC, VS, all made using what? The same building block, that is the op amp. Of course, in all the circuits we have what? Negative feedback. So you can generalize this, discussion and make a statement that if you have one type of dependent source, it could be any dependent source, then by using proper negative feedback, you can always implement any other type of dependent source. If you have one type of dependent source, you can always come up with any other type of dependent source using what? Negative feedback. That is the power of negative feedback. Okay. Okay. So this is a given circuit, and here we have the load. I'm not saying what type of element or what is the nature of the load. Okay, it is some load. Okay, the question is what is the behavior of the circuit with respect to the load. That means what? From the load point of view, how does the rest of the circuit behave like? Does it behave like ideal current source or ideal voltage source or some type of control source? That is what you should decide. Okay, let's do the analysis and decide what the behavior of the circuit would be with respect to the load. Okay. Okay, Vipin Kumar is saying it is VCCS. Very good. That's correct. With respect to the load, the given circuit behaves like a voltage controlled current source. Others also, please tell me what your answer is. Okay, anyway, please look at the screen, all of you. First, do you all agree that the op amp is in negative feedback? It is obvious, right? Because the output of the op amp, it is connected toward the minus input terminal only. So the op amp definitely it is in negative feedback. So ideal op amp in negative feedback, we can use what the concept of virtual short, which is V plus equal to V minus. What is this current? 0. What is this current? 0. So this current is also 0. Now because this current is 0, what about these two currents? Are they not equal? What is the voltage at this point? Vs. Now because R1 and R2 have the same current, they are in series. What is the voltage at this point? Vs R2 by R1 plus R2. Now which point is this? Is it not the plus input terminal? So what is the voltage at the plus input terminal? Vs R2 by R1 plus R2. So what is the voltage at this point? Again Vs R2 by R1 plus R2. So what is this current? This voltage minus 0 divided by R3. Let us call the current through the load as what? IL. IL is what? The load current. Now because at this point this current is what? 0. IL, will it not be equal to this current? Let us call this current as some I3. So here the point is what? The load current is equal to what? The current through this R3 denoted by I3. Now what is the expression for I3? The voltage divided by resistance. So Vs times R2 by R3 times R1 plus R2. Vs times R2 divided by R3 times R1 plus R2. That's all. This is the expression for the load current. Now what is the observation that you should make? Please look at the expression for the load current. Does it contain anything related to the load? It contains what? Vs, it contains R2, it contains R1, it also contains R3, but it does not contain anything related to the load. That means IL is independent of the load. So whatever be the load, IL will be the same. That means IL is independent of the load. When will the load current be independent of the load? Only when the load is connected across an ideal current source. Yes or no? That means with respect to the load, the rest of the circuit, meaning this entire thing with respect to the load, the rest of the circuit behaves like what? Ideal current source. But then if you look at the expression for the load current, does it not depend on Vs? So if you vary this Vs, it will directly affect the IL or the current flowing through the load. So this voltage will affect the current flowing in the load. So one voltage controlling another current. That is why it is what? Voltage controlled current source. So as you rightly said, it is what the voltage controlled current source. So in this way, any given circuit, you should be able to decide how the circuit is going to behave with respect to the load. Okay. So there is the discussion on how to make any type of dependent source using the given dependent source. So what is given for us? We have the op amp with us, which is a voltage control voltage source. And I have illustrated how we can make the other three remaining dependent sources using the same op amp in negative feedback. Okay. Now let me explain how we can find the input and output resistances of any given amplifier. So if you recall, I said what? Any amplifier, whatever be the type of amplifier, will be characterized by three parameters. Number one is what? Gain. Apart from gain, we also have the input resistance and the output resistance. Okay. So this is a discussion on finding Rn and Rout of any amplifier. Finding Rn and Rout, the input resistance and the output resistance of any amplifier. Now what is that input and output resistance? First of all, any amplifier, we know it's a two-port network, yes or no? So any amplifier can be represented by a box with an input port on one side and an output port on the other side. And then let's say you are standing here and you are looking in this direction. That means what? You are looking into the input port. So looking into the input port, whatever equivalent resistance you are going to see, that is what we call the input resistance. Similarly, you can also stand here and you can look in this direction. If you are looking in this direction, it means what? You are looking into the output port. Again, looking into the output port, whatever equivalent resistance you will see, that is nothing but the output resistance. So this is how we have defined the input and output resistances previously. Okay. Now let us slightly modify our definitions of Rn and Rout. Okay. Let us take the case of a voltage amplifier. Let us say this box is what? A voltage amplifier. So this box, it is what? A voltage amplifier. So obviously this is the input port, this is the output port. What source will be connected across the input port? Some input voltage source will be connected, yes or no? Vs is what? The input voltage source connected across the input port of the voltage amplifier. And in general, any voltage source will have some internal resistance in series. Even for this voltage source Vs, let there be some internal resistance in series denoted by Rs. That's all. Now the input source is what? Connected across the input port. Now if I ask you which is the input source, you should not say it is just Vs. You should say it is Vs along with Rs, because Rs belongs to the input source. Yes, and Rs belongs to the input source. Rs is not property of the amplifier. Anything that belongs to the amplifier will be there inside the box. I hope this point is clear. Any property of the amplifier will be modeled and will be present inside the box. Anything that is outside the box does not belong to the amplifier. So if you recall, the input resistance, is it not shown inside the box? Because input resistance is what? For the amplifier. Even the output resistance, it is shown inside the box. Even the dependent source, for example, voltage control voltage source, A times Vin, that is also shown inside the box. Because all these things, gain, input resistance and output resistance, all are properties of the amplifier. So they will be present inside the box. Whereas this RS, it does not belong to the amplifier, it belongs to the source. So if I ask you which is our source, you should say Vs along with Rs. This is what is our input source. And across the output port, generally we connect what a load. Or if it's a cascade of amplifiers, this output port of this amplifier should be connected across what input port of the next stage. That is in case of cascade. But here, let's say we only have a simple load resistance. So now if I ask you which is our load, obviously RL is what our load. Okay. Now what does the input source do? What does the input source do? The input source will always continuously look in this direction. Input source looks towards the right. If the input source is looking towards its right, is it not looking into the input port? And what does the load do? The load will always look in this direction, which means the load is continuously looking into the output port, whereas the input source is what continuously looking into the input port. So here input source looks into the input port, whereas the load looks into the output port. Input source looks into the input port and the load looks into the output port. So when the input source looks into the input port, whatever equivalent resistance the input source will see, that is what is the input resistance. So there is our new definition for Rin. So what is Rin? Rin, it is the R equivalent resistance seen by the input source, because the input source looks into the input port. Yes, so when the input source looks into the input port, whatever equivalent resistance the input source will see, that is what is the input resistance. Okay. Similarly, the output resistance R out can be defined as, it is the R equivalent or the equivalent resistance seen by whom? By the load. It is the R equivalent or the equivalent resistance seen by the load. Okay, because what is the load doing? Load is continuously looking into the output port. So when the load looks into the output port, whatever equivalent resistance the load will see, that is the output resistance. I hope these two new definitions are clear. So what is the input resistance? It is the equivalent resistance seen by the input source. And what is the output resistance? It is the equivalent resistance seen by the load. Okay. Now to find this equivalent resistance in any linear network, we have a very standard procedure which is also used in finding the Thevenin equivalent of any linear one-port network and so on. Okay. So we'll just borrow a little bit from Thevenin's theorem. Then we'll come back to this discussion on R in and R out. Okay. So if you have a linear network, let's say inside the network we have some independent voltage sources, some independent current sources, some resistors, and also some linear dependent sources. Remember, the network has to be linear. Okay. And let's say for this network we have a set of two terminals which will obviously form a port. Yes or no? Because this network is not a closed volume. So whatever current enters the box at one terminal, the same current must leave at the other terminal, which will definitely satisfy the requirement for two terminals to form a port. Okay. Anyway, let us say across this linear one port network we connect some load resistance. Now what will this load do? What will this load do? This load will look in this direction. So when the load looks into this box or the network, the load will find some equivalent resistance. So what is the goal? It is to find R equivalent seen by RL. So when the load looks into this one port network, what is the equivalent resistance seen by the load? For that, the procedure is the following. Okay. So to find the equivalent resistance seen by the load, replace the load with a voltage source VT. Look at this original circuit across this one port network. We had the load. What are we trying to find? We are trying to find the equivalent resistance seen by the load. And for that, you should replace the load. Because why load? Because you are finding R equivalent seen by RL. That is why replace RL with a voltage source VT. Let the current flowing out of the plus terminal be some IT. And inside the box, all the independent sources, you make them 0. First, let me draw all the elements. So there is the same box, and while finding this equivalent resistance, you have to make the independent sources 0. Let the dependent sources remain, let the resistors remain. It is only the independent sources. Okay, Srinivas is asking, what's the difference between the terms cascade and cascode? Okay, we'll come to that when we study BJT amplifiers. Cascode is a special case of cascade. Cascade is a very general thing. Cascade means what? If the output of one stage is connected as input for the next stage, then we call it what? Cascade. Yes, cascode is a special case of cascade where you cascade common emitter with common base. So if you cascade common emitter with common base, that means what? First stage is common emitter, second stage is common base. That combination is called as what? Cascode. So cascode is a special case of cascade, or you can also say cascade of common source and common gate. In case of FET amplifiers, common source and common gate combination is called as cascode. In case of BJT amplifiers, common emitter and common base combination is called as cascode. So cascode is also a special case of cascade. So because it has got tremendous application and significance, that combination has got a special name for itself, which is cascode. Okay. Okay. So coming back to this, finding the equivalent resistance. What are we trying to find? We are trying to find the equivalent resistance seen by the load when it looks into this one port network or the box, for which we have replaced the load with a voltage source VT. And then the current flowing out of the plus terminal is what? IT. Inside the box, whatever independent sources we have, all those independent sources, you should make them 0. All voltage sources, you should make them short. All current sources, you have to make them open. Then R equivalent is simply equal to what? VT divided by IT. Yes. Replace the load with voltage source VT. Let IT be the current flowing out of the plus terminal. So always be careful about the direction of IT. IT should flow out of the plus terminal of VT. Then you have to make all the other independent sources 0. Then your R equivalent is what? VT by IT. That's all. So using this method, we can find the equivalent resistance seen by any element, or you can find equivalent resistance across any element. You can also find input resistance, output resistance. Any equivalent resistance in a linear network is always found using this approach. At least I use this approach always for finding the equivalent resistance. Okay. So you might be required to find R equivalent across any element. In this case, we are finding R equivalent across RL. In some other question, maybe you are required to find R equivalent across some other element, across a current source or across a voltage source. Whatever be the element across which you are trying to find the equivalent resistance, replace that element. Whatever be the element across which you are trying to find the equivalent resistance, replace that element with a voltage source VT and then find VT by IT. Understood? In this case, because we are finding the equivalent resistance seen by the load, we are replacing load with voltage source Vt. Of course, you have to make the independent sources 0 and so on before finding Vt by It, which becomes what? The equivalent resistance. Okay. Oh. So what is our original agenda? It is to find Rn and Rout, yes or no, of any given amplifier. So first is what? How you find the input resistance. Already we defined input resistance, right? Where input resistance is what? It is the equivalent resistance seen by the input source. To find the equivalent resistance seen by any element, you have to replace that element with voltage source Vt and then find Vt by It. So here, if you want to find the input resistance, because input resistance is what? The equivalent resistance seen by the. Okay, Vipin Kumar is asking, sir, is Rn containing RL term or no? It can contain RL. It depends on the circuit. It is possible that the input resistance can depend on RL. Okay. In many circuits, Rn does not contain RL, but in some circuits, it is possible. Okay. If the circuit has feedback, then it is possible that Rn will contain RL. Okay. Anyway, so Rn is what? The equivalent resistance seen by the input source, for which you should replace the input source with voltage source Vt. So replace input source with Vt and find Vt by It. In this, in this example, when I say input source, I mean Vs along with Rs. When I say input source, I mean what? Vs along with Rs. Okay. See. So once again we have the same thing. I said what? To find the input resistance, you should replace the input source. Look at this. I have replaced the input source with what? With a voltage source Vt. Let the current flowing out of the plus terminal be some It. Then your input resistance is what? Vt divided by It. Input resistance is what? Vt divided by It. That's all. So in this, using this method, you can find the input resistance of any given amplifier. Just replace the input source with a voltage source Vt and then find Vt divided by It. Okay. Okay. What is the other thing you should find? We must also find the output resistance, finding Rout. Again, what is that Rout? What is Rout? It is the equivalent resistance seen by the load. To find the equivalent resistance seen by the load, you should replace the load with a voltage source Vt and then find Vt by It. Yes or no? Replace load with Vt and find Vt by It. But while finding the output resistance on the other side, that is on the input side, you will have the input source. I told you what, in this method of finding what equivalent resistance, the only voltage source that should be present is what? This voltage source VT. All other independent sources, you have to make them 0. Okay. So in case of finding this output resistance, whatever input source you have at the input port, that input source you have to make it 0. So make input source 0. Now that input source is what? Not just Vs, right? Input source is what? Vs along with Rs. Only that Vs part you should make it 0. If there is Rs, let it remain. Let Rs remain. So if at all the input source has some internal resistance, don't touch that internal resistance. Only that source part you make it 0. Okay. So look at this. Again, we have the same, voltage amplifier with an input source and the load. What are we trying to do? We are trying to find the output resistance. Okay. To find the output resistance, you have to remove the load. Look at this. I have removed the load. And then in place of load, you have to connect a voltage source VT. Let the current be some IT. And then I said make this input source 0. Only this Vs part you have to make it 0. That's all. R out is what Vt divided by It. So in this way, you can easily find the input and output resistances of any given amplifier. So to find the input resistance, you should replace the input source with voltage source Vt and then find Vt by It. And to find the output resistance, replace the load with voltage source Vt, again find Vt by It. Don't forget to make the input source 0. In this case, that Vs, you should make it what? 0 or short circuit. Okay. Okay, look at this, all of you. Look at this yellow color box. If I ask you what is this yellow color box, you should say it is what? Voltage source. Is it ideal voltage source or non-ideal voltage source? Because of this Rs, it is what? Non-ideal voltage source. So this box, it is voltage source, but it is what? Non-ideal. Now if I ask you what is the output resistance in this circuit, please type in the chat box what is the output resistance in this simple circuit. What is the output resistance? Sorry. Vipin RS, Srinivas RS, Nipun RS, very good. Keshav RS. I mean, there's nothing in this. It is RS. Because what is output resistance? Output resistance means what? Equivalent resistance seen by the load. Yes or no? Equivalent resistance seen by the load. Where is the load? RL is the load. Load will look in this direction. When the load looks in this direction, the only resistance load will say is what? RS. Yes or no? The only resistance load will say is what? RS. So without doing anything, you can directly say that the output resistance is what? RS, as you all rightly said. So R out, it is what? RS. Or if you want, you can also follow the general procedure of finding R out. What is that procedure? Let me quickly illustrate. So we have the original thing, Vs in series with Rs, and then we have the load resistance. To find the output resistance, I told you what? Replace the load with a voltage source Vt, let the current be some It. You have to make this independent source 0. Yes or no? This Vs, you have to make it 0. It becomes what? A short circuit. Then the only element is what? Rs. So what is Vt by It? That is what RS, and this Vt by It is nothing but the output resistance. Even by observation, we wrote the same thing, that is R out equal to what? RS. Now, when will this box behave like an ideal voltage source? Is it not for RS equal to 0? Yes or no? If RS becomes 0, then internal resistance of the voltage source becomes 0, which is true only for ideal voltage source. So if the box becomes what? An ideal voltage source with respect to load, then RS will become 0, then R out will also become 0. So the point is what? If the circuit behaves like an ideal voltage source with respect to load, then directly we can say R out is how much? Please fill up this blank. If any circuit behaves like an ideal voltage source with respect to the load, what is the output resistance value? Please type in the chat box. No, you are not getting my question. If the circuit behaves like an ideal voltage source with respect to load, then what is R out? It is 0. It is 0. Very good. Yes. Srinivas, Vipin, Nipun. Correct. It is 0. Okay. Because when will this yellow color box become an ideal voltage source? Only when RS is 0. And if RS is 0, even output resistance will become 0. So if you find that any circuit behaves like an ideal voltage source with respect to load, directly you can say the output resistance of that circuit is what? 0. But how do you determine if any circuit behaves like an ideal voltage source with respect to the load? For the circuit to behave like an ideal voltage source with respect to load, what is the requirement? Load voltage should be independent of load resistance. Yes or no? In any circuit, if you find that the load voltage is what? Independent of load resistance, then the conclusion is what? That the circuit behaves like ideal voltage source with respect to the load. So directly we can say R out is what? 0. I hope it is clear. Okay. In the same way, let us also consider the current source. Once again, what is this yellow color box? Is it not a current source? Because inside the box we have this IS, that is what the current source. But along with IS, there is also this RP connected in parallel, which is like the internal resistance of the current source. So because of RP, it is not an ideal current source. It is rather a real or a non-ideal current source. So I would write non-ideal current source. Once again, if I ask you what is the output resistance? Output resistance by definition is what? The equivalent resistance seen by the load. So when the load looks in this direction into this yellow color box, the only resistance it can see is what? RP. So what is the output resistance? It is RP. Now if the current source is what? Ideal, what is the value of RP? If the current source is what? Ideal, then RP will tend to what? Infinity. Then R out, which is equal to RP, also will tend to what? Infinity. Yes or no? If this yellow color box becomes an ideal current source for which RP should tend to infinity, even the output resistance will tend to what? Infinity. Okay. So again the point is what? If the circuit behaves like what? Like an ideal current source, like an ideal current source with respect to load, then directly we can say R out is how much? Will it not be infinity? Very good, very good. R out is what? Infinity. If the circuit behaves like ideal voltage source, then directly we can say R out is what? 0. If the circuit behaves like ideal current source with respect to load, then directly we can say R out will be infinity without doing that VT-IT method. Okay. So how can you find if any circuit behaves like an ideal current source with respect to load? What is the condition or requirement for the circuit to behave like an ideal current source with respect to load? Load current must be independent of load resistance IL. If at all you find it to be independent of RL, then the conclusion is what? That the circuit behaves like an ideal current source with respect to load, in which case directly we can say that the output resistance will tend to what? Infinity. Okay. So that's all. So this is the complete know-how about finding Rn and Rout. Okay. So let us take the non-inverting amplifier. So for the non-inverting amplifier, already we know the gain is what? 1 plus R2 by R1, which is positive. I told you what, for any amplifier apart from gain, there will also be Rin and Rout. Let us find the input and output resistances of the non-inverting amplifier quickly. Plus, minus. This is the input source gain. V0, R2, R1. Is there a load in this circuit? There is no load, right? Load means what? That RL. So whenever in any circuit there is no load, you can always connect the load between output and ground or across the output port. Yes, between output and ground, let us connect a load resistance, and this is what? V0. Okay. And what is the goal? It is to find Rin as well as Rout, the input and output resistances. What is the input resistance? Is it not infinite? Because what is the method of finding input resistance? Equivalent resistance seen by the input source. Yes or no? In fact, So to find the input resistance, we have to replace the input source with Vt like this. Let the current flowing out of the plus terminal be some It. What is this current? Because the op amp is what ideal, this current is what 0, which means It is what 0. If It is 0, whatever be the value of Vt that you apply, Vt by It, will it not tend to infinity? Anything by 0 is what infinity. So what is the input resistance of the non-inverting amplifier? It is infinity. Okay. Go back to the previous slide and let us find V naught. Let us find V naught. You say, what is the voltage at this point? It is Vn. What is this current? 0. Because ideal op amp input current is 0. So these two currents are not equal, which means R2 and R1 still they are in series. So from voltage division, what is the voltage at this point? V naught R1 by R1 plus R2. Which point is this? Minus input terminal. Which point is this? Plus input terminal. Virtual short means what? V minus equal to V plus. So V naught times R1 by R1 plus R2 is equal to what? Vn. So this is something we have already done earlier. Okay, but still I'm doing it again. So V naught equal to what? Vn times 1 plus R2 by R1. As we expect, the gain of the inverting amplifier, non-inverting amplifier is what? 1 plus R2 by R1. Now what is this V naught? This V naught, is it not the voltage across the load resistance? So V naught is not just the output voltage, it is what? The voltage across the load resistance. Now look at the expression for the output voltage or the voltage across RL. In the expression for V naught, there is Vn, there is R1, there is R2, but there is no RL. That means load voltage is what? Independent of load resistance. In what circuit load voltage will be independent of load resistance? Only when the circuit behaves like ideal voltage source. So with respect to load, circuit behaves like what? CKT for circuit. Circuit behaves like ideal voltage source with respect to load. Circuit behaves like ideal voltage source with respect to load. The moment you know that if the circuit behaves like ideal voltage source with respect to load, immediately we can say the output resistance is what? 0. So because the load voltage is independent of load resistance, the conclusion is what? The circuit behaves like ideal voltage source with respect to load. Due to that, directly we can say the output resistance is what? 0. What is the input resistance? Infinite. What is the output resistance? It is 0. What is the overall gain of the non-inverting amplifier? 1 plus R2 by R1. Okay. The same way, for the inverting amplifier, let us find the input and the output resistances. So already we know that for the inverting amplifier, the gain is what? Minus R2 by R1. So this is what R1, this is what R2. This is our output voltage. Again, in this circuit, there is no load. In any circuit, I told you what, if there is no load, you simply connect the load RL between output and ground. So between output and ground, you connect this load resistance RL. Now the circuit is what? Complete. Okay. Again, let us find Rn and Rout. So first, let us find the output voltage itself. Okay. What is the voltage at this point? 0 due to virtual short, because V plus is 0, even V minus would be 0. Here it is what? V in. Here it is what? V naught. What is this current? 0. What is this current? Let it be I1. What is this current? Let it be I2. Now at this point, I1 is entering, I2 is leaving. So I1 equal to what? I2. What is I1? Vn minus 0 by R1. or V in by R1. What is I2? 0 minus V naught by R2, which is minus V naught by R2. So what is V naught by V in? It is minus R2 by R1. What is V naught by V in? It is minus R2 by R1. This is something we already know. Inverting amplifier, the gain is what? Minus V naught, minus R2 by R1. So from here, V naught can be written as what? V in times minus R2 by R1. Again, this V naught, is it not the voltage across the load resistance? Yes or no? This V naught, it is nothing but the voltage across the load resistance. And if you look at the expression for the V naught, which is the voltage across the load resistance, again, there is no RL, which means the voltage across the load does not depend on the load resistance. So is it not like load voltage is independent of load resistance? Load voltage independent of load resistance, circuit behaves like ideal voltage source with respect to load, which means directly again we can say that R out is what? 0. That R out is what? 0. So for the inverting amplifier, just like the non-inverting amplifier, R out is what? 0. Now we should find the input resistance. So let me draw the same circuit again. So this is the same circuit. That is what the inverting amplifier. Now we are trying to find the input resistance. What is the method of finding input resistance? I told you what, replace the input source with a voltage source Vt. Yes or no? Replace the input source with a voltage source Vt. Current flowing out of the plus terminal is what? It. Now you should find Vt by It. Again, the op amp is in negative feedback. So what is the voltage at this point? Due to virtual short, 0. What is the voltage at this point? Vt. What is the current through R1 in this direction? Vt minus 0 by R1, which is Vt by R1. So this current and this current are not equal. So It equal to what? Vt by R1. So what is Vt by It? It is nothing but the input resistance, which is equal to what? R1. So for our inverting amplifier, what is the overall gain? Minus R2 by R1. What is the input resistance? It is R1. What is the output resistance? It is 0. Whereas for the non-inverting amplifier, the input resistance is what? Infinite. And the output resistance is what? 0. Now let us make a quick comparison between the two basic amplifiers, the non-inverting and the inverting amplifiers, and find out which one is a better voltage amplifier. Okay. So for the non-inverting amplifier, what is the gain? 1 plus R2 by R1. For the inverting amplifier, what is the gain? Minus R2 by R1. For the non-inverting amplifier, what is the input resistance? Infinite. What is the output resistance? 0. For the inverting amplifier, also output resistance is what? 0. And the input resistance, it is what? R1. Yes. Right now, both the amplifiers are what type of amplifiers? Both are voltage amplifiers, because for the inverting amplifier, input is voltage, output is also voltage. Same for non-inverting amplifier, both are voltage amplifiers. We know from the very first class that for a voltage amplifier, ideally, the the input resistance should tend to what? Infinity, and the output resistance should tend to what? 0. These are the ideal values of, the Rn and Rout of a voltage amplifier. So if you look at the non-inverting amplifier, input resistance is what? Infinity. Is it not same as the ideal value, which is very good? Even the output resistance is what? 0, same as the ideal value. So for the non-inverting amplifier, both the Rn and Rout values are exactly equal to their ideal values. But for the inverting amplifier, the output resistance is what? 0, which is same as the ideal output resistance value, which is very good. But the input resistance, it is only R1. It is not infinity. Ideally, for a voltage amplifier, input resistance must be infinity. But here, it is not infinity. It is finite and equal to what? R1. And for a good voltage amplifier, input resistance should be as large as possible. Ideally, infinity. You try to make Rn as large as possible. So for the inverting amplifier, how do you make input resistance larger? By increasing the value of R1, because Rn is what? Equal to R1. When you increase the value of R1, input resistance will become larger, which means it becomes what? A better voltage amplifier. But what is the magnitude of the gain for the inverting amplifier? Magnitude of the gain is what? R2 by R1. Actual gain is what? Minus R2 by R1. Magnitude is what? R2 by R1. So when you try to increase the input resistance by increasing the value of R1, what will happen to the magnitude of the gain? Will it not decrease? Yes or no? Because R2 by R1, if R1 increases, the overall ratio will decrease. But for a good voltage amplifier, even gain should be as large as possible. So for the inverting amplifier, if you make an attempt to increase the input resistance, then your gain will decrease. So look at this. Input resistance, if you try to increase it, your gain will decrease. So this is what we call trade-off between gain and input resistance. So in case of the inverting amplifier, you have a trade-off between gain and input resistance. You have a trade-off between gain and input resistance. But for the non-inverting amplifier, you don't have any such trade-off, because input resistance is what? Always infinity, which is the ideal value. Yes. But for the inverting amplifier, if you try to increase the input resistance, your gain will decrease. Yes. Ideally, for a good voltage amplifier, gain should be large, even input resistance should be large. But here, if you try to increase the input resistance, your gain will decrease and vice versa. That is what we call trade-off between gain and input resistance. Now, the final conclusion is what? Between the non-inverting and the inverting amplifiers, which is the better voltage amplifier? Clearly, it is what? The non-inverting amplifier, because there is no trade-off, etc. So between the two non-inverting amplifier is the better voltage amplifier between the two. So between non-inverting and inverting amplifiers, which is the better voltage amplifier? It is the non-inverting voltage amplifier. So that's all. So this is just to illustrate how one can easily find the input and output resistances of any given amplifier or any given circuit for that matter. So I'll stop for today. I hope everything is clear up to this point. So we are almost close to winding up negative feedback. You see, for the op-amp, there are three cases. Okay, op-amp can be used in negative feedback. Op-amp can be used without any feedback. Op-amp can be used in positive feedback. So far we have been looking at op-amp used in negative feedback. In fact, more than 90% of the op-amp circuits are based on negative feedback. That is why we are emphasizing so much on negative feedback. So from tomorrow onwards, we'll start looking at the other two use cases, which are op-amp without feedback and also op-amp in positive feedback. I hope everything is clear up to this point. Good night.